In the previous episode, we derived the Einstein field equations which describe how gravity works around massive objects. One of the results of Einstein's theory of relativity is that when you are near a supermassive object, the time that you measure will slow down relative to the time measured by someone far away from the supermassive object. We can apply this knowledge to a practical problem. Let's say that your dad went to the store to buy some milk, but he isn't coming back. Let's find out when he will come back while including the slowing down of time caused by your mother's huge mass. So, the equation which describes time dilation due to gravity is as follows, where T0 is the time measured by your father while he's under the influence of your mother's gravity, T is the time measured by you who are isolated in your room, unaffected by your mother, capital G represents the gravitational constant, capital M is the mass of your mom, capital R is the distance of your between your father and your house, and C is the speed of light, which is constant. So, by analyzing this formula, you can tell that the closer your father gets to the household, the smaller T0 gets. Actually, it approaches 0. Which means that as time goes on, your father becomes trapped in time. But to get a more clear view of this, let's see his equation of motion. So if your dad is walking with a constant velocity, let's call it v, then by the definition of velocity, it's the derivative of position with respect to time. So what's important is that the velocity we're talking about here is the velocity of your father in his reference frame. So that's why here it's dt0. We are taking the derivative with respect to your father's time. But by using the formula above, we can write this formula within your reference frame. So dr over dt times this whole square root So let's multiply both sides by this square root, and we get the following formula. And as it turns out, this equation right here is in fact a differential equation, because we have a function r, which is a function of time. Your dad's position depends on time, but at the same time, this equation also involves the rate of change of your father's position. So, differential equations in general are pretty difficult to solve, but this one is pretty straightforward in fact. So, let's square both sides and get that v squared times square root squared will cancel out, so you just get this. This as in what's inside the square root equals dr over dt whole thing squared. So it's quite uncomfortable. We find it quite uncomfortable that the function that we're looking for is in the numerator. So what we can do is multiply both sides by r and get that v squared times r equals 1 minus 2gm r over c squared, which equals r times dr over dt thing squared. Now, let's multiply out the bracket on the left hand side and see what we get. v squared times r minus 2gm v squared over c squared. The r from here cancelled out with the r from here. That's why there's no r here. And as you can tell, in fact, this whole term is constant. G is a constant. Your mother's mass is constant. Your dad's velocity in his own reference frame is constant, and the speed of light is constant. And we can also write the right hand side. dt squared. Now, we can tell that there's repeating a common factor here of r. So let's bring this expression to the left hand side and get the following result. minus 2gm v squared over c squared equals 0. Now, we can factor out the r here and bring this term to the other side. R v squared minus dr over dt squared equals 2gm v squared c squared. Now, if I were to divide both sides by this bracket, then on the left hand side I would just get r, and on the left hand side I would get constant divided by some function of dr over dt. So let's use common physical notation and let's denote dr over dt as r dot. And now let's also divide both sides by the bracket using already what we have, r dot squared. And here's what we will get. R equals 2gm v squared over c squared times 1 over v squared minus r dot squared. So we have played around with the formula. It's still a differential equation which doesn't seem solvable, but there's one thing we can do to greatly simplify the problem, namely differentiate both sides with respect to time, d over dt. So when we apply d over dt to the left hand side, we get dr over dt, which we can write as r dot, as we mentioned before. And the left hand side, we get the derivative of the expression on the right hand side. So we can take the constant out, as we mentioned. This whole thing is constant, and we get d over, let me write it in a special color, 1 over v squared minus r dot squared. So here, for this derivative, we will have to apply the chain rule. So first we will take the derivative of the function with respect to r dot, and then we will take the derivative of r dot with respect to t. So what it comes down to is the following. You can write v squared minus r dot squared as, let's write it somewhere here as a note, 1 over v squared minus r dot squared equals v squared minus r dot squared to the power of minus 1. So now it's quite straightforward. The derivative, it's the old exponent times the whole function. Exponent has been reduced by 1, so from minus 1 it went from minus 2, times the derivative of the whatever is inside. So it's gonna be 2r dot, and now the derivative of r dot with respect to time, which is just dr dot over dt. Now let's close the bracket, and we can see that there's some stuff repeating, namely there are two minuses, which will give a plus. There's also a 2, which we can multiply with the 2 over here, and there's also a common factor of r dot on both sides, which we can cancel out. So if we cancel out the r dot and do the multiplication, we get that 1 equals 4g m v squared over c squared times v squared minus r dot squared to the power of minus 2 times dr over dt. So now what we have accomplished by doing this whole differentiation process is that this equation has actually now turned into a whole different differential equation. Now it's a differential equation where the variables time and r dot can be separated. So if I were to multiply both sides by r dot, then on the left hand side I would just have the expression with dt, and on the right hand side I would only have expressions related with r dot. So let's multiply both sides by dt and also divide by this whole constant term. So what we get out of this is c squared over 4 g m v squared times dt equals v squared minus r dot squared to the power of minus 2. Let's write it again in the more obvious form, namely this one. We have, in a way, reverted back what we did. We came back to this form. And this whole thing, oops, there's supposed to be to the power of 2, not to the power of minus 1. That's why we did the whole flip. And dr dot. So now we can integrate both sides with respect to their variables. On the left hand side, we get a rather straightforward integral. So it's c squared over 4gm v squared is just a constant. So you have an integral of dt, which as we know is t plus some arbitrary constant of integration. So we can evaluate the integral here. So it's c squared 4gm v squared t plus some arbitrary constant, let's call it k1. And the left hand side integral is more difficult. Let's write it one more time. Squared dr dot. Let's call this I for the time being and play around with I. So let's see, how can we simplify this expression? It looks rather difficult, but there are a few tricks we can apply here. So first things first, we can factor out the v squared from this and get v squared 1 minus r dot squared over v squared whole thing squared. So by applying exponent rules, 2 times in fact, we can get, but it's dr over dr v to the power of 4 times 1 minus r dot divided by v whole thing squared, and this whole thing squared once again. So this integral is of course solvable. You can find an analytic solution to this one, but it's going to be very long and complicated, and it will not really help us to progress in the problem any further. So let's go a few steps back, namely to the formula for our time dilation. So as our father gets closer and closer to the household, the time slows down. But by this expression, because of this formula, it means that dr over dt will become lower and lower and lower. Our father starts moving slower and slower relative to us. But v remains constant because from your father's perspective, he is moving at a constant rate. So that means that dr over dt, which we called r dot, is getting smaller and smaller and smaller, getting close to 0, while v remains constant. So that means, let's get back to our integral, that dr, let's write it somewhere here with a special color, r dot is really small relative to v. So that means that r dot over v is really, really small. We can approximate r dot over v to be approximately equal to 0. Then the integral simplifies quite nicely. So this whole thing is almost equal to dr dot, dot, divided by v to the power of 4 times 1 minus 0 to the power of 2 to the power of 2, which is just the integral. Also, v to the power of 4 is a constant relative to r dot, so we can pull it out before the integral sign. So this is 1 over 4 to the power v to the power of 4 integral of dr, which is just 1 over 4 to the power v to the power of 4, excuse me, times r, plus an arbitrary constant of integration, but we have already included it for the integral with respect to time, so we do not have to include it here. So now that we have approximated this integral, let's go to our original equation. And what do we get? We get that c squared over 4g mv squared t plus arbitrary constant k1 equals 1 over v4 times r dot. So here it's a bit uncomfortable that we have a constant k1, so we would like to get rid of it somehow. So here we can apply the so-called initial conditions. So if we are wondering what happens to our dad right when he comes back from the store, he bought his milk and now he's coming back home. At that point we can say that t equals 0. So for t equals 0 we get, so this whole part disappears, and we get that k1 equals 1 over v4 r dot. So when our dad is in store, then we expect him to be safe from the gravitational effects of your mother. So that means that r dot is very close and in fact equal to v. So let's write that down. R dot equals v. So when we apply it here, we get that v over v4, which equal 1 over v cubed, which is our k1. So now we can use this knowledge in this formula and finally solve for r. So if you write r dot as dr over dt, as it was called so originally, we get that c squared over 4g v squared, if I remember properly. Yes. T plus, now we know what k is. It's 1 over v cubed. And this is equal to 1 over v4 dr over dt. And once again, we have a differential equation with separated integral variables, so we can multiply both sides by dt. In fact, we can also multiply both sides by v4. It will be very useful, as many things will cancel out. So once we do that, we get c4 times v squared 4g m times t. You see v squared cancelled out with c4, which gave us c squared, this time in the numerator. So also similar thing happens here, we just get v, and this whole thing dt equals dr. So if we integrate both sides, we get the following. Let's have this integral sine b. That's nice enough. So on the right hand side we get a rather obvious integral, that's just r. And on the left hand side we have an integral of a linear function which results in a quadratic. So this whole integral is equal to c squared v squared over 8g m t squared plus vt plus some arbitrary constant of integration, let's call it k2. So once again we have a constant that we would like to get rid of. So let's once again consider the initial conditions. So for our initial time, for t equal to 0, where is our father? So, well, obviously our father is at the store. So if we call the distance between the store and the household r0, well, let's take it step by step. So if we apply, if we substitute t equal to 0 here and here, this whole part disappears and we just get k2 equals our father's distance from the house at time equal to 0, which we can call r0, which we will identify as the distance between the shop and our father. So the whole expression for time, after using all of these techniques, is as follows. R of t, let's highlight that this is a function of time, is as follows: c squared v squared over 4gm t squared plus bt plus r naught. So this is a quadratic formula which you can use. You can use the quadratic formula for this to find when r is equal to 0, because when r is equal to 0, then that means that dad is home. So if you were to apply the quadratic formula on this one, oh, of course, to apply the quadratic formula and find an actual number, first we have to substitute these numbers. So c is known, g is known, r naught is not known, v is not known, and m is not known. So we can have some liberty and assume some numbers. So if we assume that r naught is a rather comfortable number of 1000 meters away from home, and v is a very comfortable walking space of 1 meter per second, then what is m? That's the last thing that we have to know. So the heaviest object in the universe which has been measured so far is the center of the galaxy Holmberg 15A, which has been measured to weigh as much, so mass of Holm 15A. That's the center of a full galaxy. That has been estimated to be around 4 times 10 to the power of 10 times mass of our sun. So this is the heaviest black hole that has been located in the universe. So it's pretty safe to assume that the mass of your mother is approximately equal to double of that. So if we use all of these numbers and plug it into our calculator, we find that the time when dad is supposed to come back home, our final solution will be t equals to 9.5052 times 10 to the power of 14 seconds, which is equal to... also, a quick note on the sign. Of course, when it comes to value, v is equal to 1 meter, but since dad is coming back, then we have to use the minus sign here, so that we include the fact that he's actually coming towards us, not away from us. Anyway, we can convert this time from seconds into years, and we get that dad will be back home in 30,120,161.229 years. Which seems like a big number, but it's not big enough. Namely, we have applied a series of approximations in our solution. First of all, the most obvious of approximations was approximating this approximation. R dot over V is approximately equal to 0. That's the first approximation that we did. But there's one more issue. There's one more issue with our approach. The formula that we started off with, T naught equals T times the square root of 1 minus 2gm over RC squared. This formula only works when you're outside the Schwarzschild radius of the object you're studying. And since your mother is this goddamn heavy, then this whole formula breaks, and we conclude that your father is never coming back home. That's it, folks.